everybody. This first video on polynomial long division is kind of an introduction to the concept, or not the concept really. We are very familiar with long division, hopefully by now. But it just kind of shows the uses. You already noticed that I wrote at the top there, why do this, okay? So essentially what I'm going to tell you is this, and in terms of my opinion, long division, and we'll be doing synthetic division, are most useful when we're trying to search for the zeros of a polynomial function, okay? And so let's start by talking about the rationale here. So you'll notice that I've written a function, f of x. We've got a cubic here, third degree thing, so it can have at most 3 real zeros, you know, at most 2 turnaround spots, and we can determine like the end behavior of this graph, you know, it being odd degree, it cannot start nor end the same. It would start down, end up, or start up, end down, and because it's got a positive leading coefficient, it must end up on the right-hand side of the graph. So what do you know? I've already graphed this, okay? So fact of the matter is, you heard me say that it is most useful to use polynomial long division when we're searching for the zeros of a function, okay? So you'll notice, looking at this, having graphed it, hopefully you have a graphing utility. If I asked you to find the zeros of this, you might notice that 2, oh my goodness, 2 is most definitely a zero of this function. So we're going to start with basically that fact. But you'll notice also that we've got a couple other zeros over here that really, you know, we can't really determine what they are. So it'd be nice if we could find a way to figure these things out. Okay. So let's head back over to Photoshop and start with the fact that we know that we have 1 0. Okay, so we're going to list this 0. We know that say 2 0 is a solution for this graph. We could also write this as, hey, if we know that x equals 2 is a solution or a root or an x-intercept or a 0 of this graph, that must imply that then x minus 2 is a factor of this graph, okay? So let's say we could like factor this original polynomial. You know, maybe we can. It looks very, very odd looking. You know, we might be able to factor it, but the bottom line is this. If we did factor it and 2 is a solution, then x minus 2 must have been one of the factors because let's face it, when you set x minus 2 equal to 0, you get x equals 2. So that'll be part of our remainders theorem in a following video, but basically, we already know a factor of this. And if you consider this, let's say, you know, I wanted to make the original polynomial less complex. Basically what I'm saying is, if we know that x minus 2 is a factor, then we could say the original polynomial f of x, must be the product of its factor x minus 2 and some other polynomial. That is, when I multiply x minus 2 times the other, say, 2 factors of this polynomial, I get the original, okay? So maybe what I'd like to do is just discover, so what must these other 2 factors be? Because if I knew those other 2 factors, then I could find the zeros. So here's going to be our method. Essentially, we're going to take the original polynomial. If I wanted to isolate, say, this quotient of x, this q of x, we could divide out x minus 2 as a factor from both sides. Now keep in mind x minus 2 because we knew 2 was a 0, so x minus 2 is a factor. If I divide f of x by x minus 2, it would just leave behind this remaining portion that, guess what, might be easier to factor than this original sloppy thing that I kind of hooked you up with over here. So if we're going to be dividing polynomials, well then we better have a method for doing so. So let's go ahead and get started. Long division. Okay, so we are going to take this knowledge of the fact that x equals 2 is a solution and x minus 2 is a factor. We are going to take f of x, like we listed on the right there, and we are going to divide it by x minus 2, which should leave behind the other remaining factors. So since we are dividing f of x by x minus 2, and I'll write this out in roster notation. We say 6x cubed minus 19x squared plus 16x. Oh, you're making me write it all. Plus 4. And we are dividing this by x minus 2. We're going to do some long division. So let's start with our long division bar. And the fact that our dividend here, okay, we have a dividend and a divisor. Our divisor is the thing we are dividing by. Okay, and the divisor, in this case, we're dividing the factor x minus 2 out of our dividend, and our dividend happens to be the original polynomial that we wanted to separate the factor from. So plus 19x squared plus 16x plus 4. This is very much like regular long division in that we're going to ask, hey, how many times does, say, this go into this guy? It's just that we're going to ask it in a very peculiar manner. And by peculiar, I mean this. All I want your eyeballs to pay attention to on this is this first term on this divisor. Sorry, I've got a phone ringing in the background. And this first term on your dividend. But what I'd like to ask is this. How many times does this x, or this first term, go into 6x cubed? Now that's an interesting question. If I said how many times does x go into 6x cubed, we could also ask this the same way, or a different way. What could I take times x to get 6x cubed? And, you know, keep that in mind. If I divided this by x, you know, I'm saying how many times does x go into this thing. That would be what I could take times x to get 6x cubed, okay? So here's going to be the first step every time we do some long division. We're basically going to look at the terms that are in the front here, the term in front of my divisor and the term in front of my dividend, and say, look, what could we multiply really this by to get it to be a 6x cubed? That's not a very hard question. I think I could take an x times 6x squared to get 6x cubed. Now, that is what I'm going to write up here. Notice that I put the x squared over these x squared. And the reason why is because we're lining up like you would with normal numbers place value. Okay? So I know that x goes into 6x cubed this many times. So what happens when you do regular long division, right? Whatever number you put up here, we end up taking times the divisor, and then that's what we're going to take away from whatever's down here. Okay, so let's take what we wrote up here, 6x squared. We are going to take that, and we're going to multiply it by this polynomial over here, this x minus 2 factor. So 6x squared times x, look at that, that's our 6x cubed. Okay, we also have to distribute the 6x squared over here to this minus 2 as well, though. So 6x squared times negative 2 is negative 12x squared. So now we've done our multiplication. Recall with regular long division, at this point we would be subtracting whatever we just wrote down here in yellow. So I want to be clear on this. I'm going to put parentheses around all of this because when we subtract it, okay, we are subtracting it all. If you were to not put parentheses around that and say minus 6x cubed minus 12x squared, you might think that this negative sign here is only associated with your 6x cubed, which of course it's not. Since it's in front of this entire parenthetical quantity, we're subtracting off everything. So my suggestion always tends to be this. We'll make this a positive, we'll distribute the negative, so this is now a negative 6, and this is a positive 12, and we'll just do some addition instead. So cool beans, man. Check this out. Your 6x cubes, they cancel, you've got none of those left. That's what we want to happen. And negative 19 of these x squareds plus 12 of these x squareds, you end up with a negative 7 of these x squareds. Okay? So again, we're treating this like regular long division. Let's go ahead and drop down this here. Okay? So we got plus 16x. Plus 16x. Here's the deal. Everything we just did, just with that regular long division, we're going to keep going until we get to the end here. But now instead of saying how many times does x go into 6x cubed, no, we're going to ask how many times does x go into negative 7x squared. In other words, what could we take times this x to get it to be negative 7x squared? Of course, the answer to that happens to be negative 7x. So this negative 7x, we'll put it up top. And of course, you notice I'm putting this x to the first over these x to the firsts because I would like my place values to line up. And just like last time when we multiplied this factor over here by 6x squared, we're now going to take it times that 7x that we had just listed. So now let's take this negative 7x, multiply it by this over here. So negative 7x times x, there's our minus 7x squared. And now negative 7x times negative 2 is positive 14x. And again, we're going to subtract all of this off. So there go our 7x squareds. You know, we can distribute this negative, positive, positive, negative. Okay. So our 7x squareds, they're gone. Positive 16x's and a negative 14x's, okay, that comes out to be a sum of 2x's. And we're going to kick down this plus 4. So now it's down, and let's start again, okay. So now this time we're asking, hey, that x, how many times does it go into this leading term? So in other words, what can we take times x to get 2x? Hey, we could take a positive 2. And notice that constant goes on top of these constants. So 2 times x, that's 2x. And then 2 times negative 2, okay, 2 times negative 2 is negative 4. Negative 4, okay? And by the way, I'd like to, go back and fix something here. And this is really lame, I'm very sorry, but this should have been a minus, which means this will be a minus here. I really wanted this to come out evenly, and so forgive me, it is a negative 4. I will remedy this situation presently. But the fact of the matter is, when we subtract this time, make this a plus, so we'll negate this here, negative, positive. Positive and negative 2x's cancel. Negative 4 and positive 4 cancel. I wanted this to happen, and again, I'm sorry. But recall from, like, I don't know, 4th grade, hey, this is our remainder. So we didn't get a remainder this time. So this has some implications. We could say, like, r is 0, and that's actually a really bad habit. We don't want to do that. But the bottom line is, it just means that this factor, it went in evenly. Okay, and it went in evenly because we knew it was a factor to begin with. It's like saying, hey, 3 is a factor of 24. So when I divide 24 by 3, I shouldn't have anything left over. So let's talk about the implications of what we just found. We know that x minus 2 being a factor went into this evenly. We also know, looking back up here, okay, x minus 2 times this leftover that we just found gives us the original polynomial. So in other words, this right here times this right here should get us back to this original polynomial. That is, here we go, this is the big thing, 6x cubed minus 19x squared plus 16x minus 4 is actually equal to x minus 2, which we just divided out, times what we just found, that leftover, 6x squared minus 7x plus 2, más dos. So why would I want to do this? Well, I'll tell you what. If I said, now, let's keep factoring, it's a little bit easier to factor this guy, as a matter of fact. No pun intended. So now we have x minus 2. We'll bring that straight down. So I need two things that multiply out to be 6x squared. So, you know, maybe we'll rock 2x and 3x in front. So now we've guaranteed we get this 6x squared. We need to guarantee we get a positive 2. And note that our terms here in the middle are going to have to sum to be a negative. So I'm thinking this is going to be negative and negative. But 2 and 1 seem to be the only factors that come to mind. So I'll put a 1 here and a 2 here, and we'll check it. Let's say I did 2x times negative 2, I get negative 4x. And then negative 1 times 3x is negative 3x. Hey, those add up to be our middle term of negative 7x. So again, hey, we just went through all this long division, and we'll talk a little bit, we'll do some more examples of long division, but the reasoning behind that was because it's a little bit easier to factor down that leftover part once you factor out something that you already knew existed, okay? And you know, if I set these all equal to 0 now, like 2x minus 1 is 0, and 3x minus 2 is 0, and of course we had x minus 2 is 0, if we're finding zeros of this function, we get, okay, x equals 2, which was one of our original zeros, but also we get 1/2 in that second equation right here. In this equation, we get 2/3. And just to verify this, you know, we could go back and look at our picture. It does seem to be 1/2 and 2/3 where our other two zeros. Okay, so we'll do some more follow-up videos, but that's basically the rationale behind wanting to do long division with polynomials. And besides the fact that, you know, like math teachers, we just want to bug the snot out of everybody. So enjoy.